Hello, my name's Chris Ryan. As you guess, I'm a software engineer doing C++, just like many of you. I'm just an ordinary guy who's practiced on a couple particular areas. I've been doing everything for everywhere forever. About this talk, I'm going to do the about me and describe what serialization is, some of the features that I'm doing that are 14, 17 compliant, and actually you'll probably go back and you could be 11 compliant also. I'm going to show you some the data structures, or how it climbs through the hierarchy of objects, some of the bells and whistles, and then modifications for doing contracts with C++ 20. And then I have what are called demos, but it's all slideware. I do have real source. I will post that on the GitHub here when I get back home. So, okay, like I was saying, I've done everything everywhere. Been doing it forever. Enough. Okay, I am not trying to sell you the use of my library. I'm going to more of teach you the techniques that I'm using in it. If you want to use pieces of it, have at it. This was a personal exploration of how can I do this, or first of all, can I, and then how can I? This actually goes back to some technology a long ways back with the Microsoft Foundation classes, MFC. They were doing this type of thing back in the early 90s. MFC is very much hated by a lot of people, but it actually had a lot of ideas ahead of its time. So I hope you gain something out of this. So the project, binary object serialization, was to climb through a series of complex data structures and serialize the data out in a binary form, very compact, very tight, trying to go for fast. Wanted it to be minimally intrusive into the classes that we add these serialization to. So I think I've done that with pretty much just adding a member function to actually serialize the data. And for multi-hierarchy layers and classes, there is some CRTP, curious template recurring template pattern. One big thing I wanted to do, MFC used a lot of macros for theirs. I wanted to do it entirely without macros. Macros are to be hated. So, what you're going to see here is mostly slideware. It is actual real running code. Some of it's poorly formatted. I took a few shortcuts for what you're going to see on the slides. There are a lot of other serialization techniques out there. Many of them very good. A lot of them spit out to text formats, JSON type of thing, which I consider creates a lot of text bloat. Huge amount of storage for just a very small amount of data. A lot of the others also do not handle loops in data structures. I will, when I store my data out, if I detect there's a loop, I just remember the object number that was there. And so when I just go to stream it back in, I can recreate it by reusing multiply used objects by their object ID. And it can be relocated somewhere else in memory. Okay, plain hierarchical data, easy enough to climb the tree through an LNR, left, right, me type of, or left, me, right kind of hierarchy through here. Everybody's done tree climbing structures before. But when you get into data structures, something like this, you quickly find yourself in funny loops and blocked and networking and yada yada. And we don't want to go recursive because otherwise you just end up serializing the same thing out over and over again. Once we serialize out an object, we remember that. So the next time we hit it, we don't serialize it again and go into recursive looping. The types of things that you can store out from any class would be an object or value, an intrinsic type, a pointer to an object, an array of objects, and you also have, there's reference to objects. But what can actually be persisted and reloaded? We got those four types. However, we could persist out a reference to an object, but we can't reload it. because a reference has to be initialized on construction. And we're not doing that. So hopefully your classes that you're gonna be serializing out won't have references in them, or you need to architect around those. And then we have the other standard container type classes, strings, vectors, arrays. I have mechanisms in there for serializing that out. What these don't handle, you can do by serializing out your own classes, which are aggregates of probably all these other smaller building blocks. Here's a frequent serialization style you may have seen before. You create a data source, or in this case, it's a files where you're gonna save this out to. You have an archive, and you just stream your objects into the archive. And when you load it, you do the reverse. You have a file source, you can give it to your archive, and you stream into it. In the class that you would save in and out of, inside the streaming mechanism, it would call serialization, and it says, is serializing? Serialize it out. Or it is storing, serialize it out, else it's loading, so it loads in. So here's the core of the archive object. Basically just have a friend operator of the shift in, shift out, and all that you need to do is turn around and tell it to save. You're all done. That's it. We can go now, right? No. But what has really happened is now we actually need to tell it what type it is we're saving and have it deduce that, and we can do that through type deduction. And here we would want to save out everything that's a type of something, everything that's a pointer to a type, and arrays of types. And you know, these are all references, even when you're storing out. We could have done not references when you were storing out, but I wanted to go for symmetry. And I also avoid using const when storing out, which would be grammatically correct. However, if you're gonna want to be able to serialize out from something, you're gonna want to serialize back into it, and you can't serialize back into a const object. So let's just make sure that that you can serialize in and out of it. And so these are the types of, they're always reference to the object. We don't want to make a copy of it. It's a reference to the pointer, and the array is actually a reference to the array. And it knows and can deduce the type and the count. Now, of the types we're going to want to store out, we can have integral data types, your different scales of ints, plain old data, which you can just do bit blitz mem copies of. And then we have is serializable and has serialized and is serializable. The distinction comes in here a little bit later. Has serialized means the class has a serialized function, and then I can call it and just call it and say serialize. Is serializable, we'll hit later for basically a polymorphic save and a polymorphic reloading and reconstructing, and we can create derived types on the fly. You can have a base pointer, save out the base pointer, and it actually saves out the furthest derived. When you go to read it back in, it can figure out not only what the base type pointer is, but what the derived data type is that it's going to be going there without an object being there, because it knows it, because it saved it out when we streamed out the data. And we'll get to that mechanism a little bit later. And if it's something that is serializable, it's derived from a serializable base class. So actually, we have some const expers for what we had just seen for those 4 different cases. And then I set up a using to abbreviate rather than saying enable if in every line in a big long string of noise and garbage. So I can just say template type, name type, if array, or pardon me, if integral type, save, and that we'll call an integer type function. If it's a plain old data, call an integer, or pardon me, call the plain old data type. I could have saved integers as plain old data, but If you're crossing platform bounds, you might have big Indian and little Indian data you're mixing. So I protect that. I always save everything out to the stream, and little Indian would be network byte order to protect, so it's always consistent. And then of course we got the has serializable and is, if has serializable and if serializable, if has serialized and if serializable. So here's a very super quick example. These are shortcutted for slideware. So if it's an integral type, I fix the byte order and I write it out. And I write out what the size, it writes out the size of the object. When you go to stream it back in, it better be the exact same data type you're reading into, and so it's gonna know the type, the size to deduce for reading back in. Plain old data works kind of the same way. You don't have to do the byte order adjustment. If you had a plain old data type, a pod that had integral data in it, you should probably manually serialize out those integers internally unless you knew you were going to be absolutely going back to the same type of platform. And then if has serializable, it calls the object and tells it to serialize itself. The archive knows whether it's loading or saving. So we'll see an example of the serialized function again that we just saw earlier. It does the switch if it's storing or not, or loading. And surprisingly, has serializable and if serializable look the same here. One is potentially a polymorphic call, the other is not. So pseudocode on saving out an array of objects is each element we treat and deduce repeatedly by using all the previous rules, but we know there's a count of them. So we save out the count, save all each elements. When we go to read it back in, we read what the count was. The array better be the same size that we're reading back into, otherwise you'd have some form of mismatch, and that would throw some nasty errors. And actually, I skip a lot of error handling in here. Verify the array size, and then read each of those objects back in, and each going to rededuce each one of those types. So this could be any type of array. It could be a serializable type object, or it could be an array of ints, or array of strings, and it will just deduce which types those are. Okay, this is a slide we saw before. We just stream out and stream back in. And my pointer working? Yeah, we got the is storing, stream out, is loading, stream in. But what if we're actually streaming out a pointer to an object? In a typical archive, if you have a pointer and you tell it to stream out, it's gonna stream what the value of that pointer is. Here, we're actually not gonna do that. It's gonna store out an object ID and then stream out the contents of that pointer, or what the pointer is pointing at. So when it goes and reads it back in, here, it's actually a null pointer that we're filling in, and it's actually gonna dynamically construct what this type of my class is, stuff one in there, and then read the data back into it. And then of course the set data is just whatever your application was doing for, I needed to show that we were using the data, the same as we did the get data above. We have a problem here. If you have a hierarchy and you're pointing at your base type and you just go to serialize it out, it will call to the furthest derived, because actually I take it back, this is not virtual here. So it would do object slicing and just serialize out what the base was. If there were virtual, it will throw to here, serialize out what the derived is, drill down, and call the base method to save its data out. Works good until we go to stream it back in. Because this doesn't have any object type ID, The only thing that it could assume was we're about to stream in a my base, and it will construct a my base and go to stream into it, which in the first scenario where this was not virtual, we would only stream back in the base, and we would actually have restore our preserved object slicing layer, which is not what we wanted. If it was virtual, it's still going to assume it's a my base, so it's going to construct a my base on the fly and serialize that in. And so we have a mismatch because we would have saved out the derived type, well, actually, and the base type. And the same way as in construction of an object, this is entirely methodological. I always want to peel the onion from the inside out. You go for the base first, store its data first, then the derived. So that's why when I do the serialize, I drill down first and then do the rest of this serializing. You didn't necessarily have to do it that way. It just is a lot nicer to do it in the same order as object construction would work, because we're effectively constructing an object on the fly. Because we just nude an object and then we're going to populate it. The way of fixing this, of when it goes to stream it back in, come on, where'd my pointer go? There, we stream back into the pointer here, is we have these layers that are called, that derives from a CRTP curiously recurring template pattern that where it knows what the object is and what its object ID is, or object type is, and we can persist that out. So when it goes to stream this back in, it says, yes, I'm going to store this in a pointer of my base, but I really stored out a my derived object. So it's going to construct, it's going to see the object ID and say, I need to construct a my derived, and so it constructs that and then calls the serialize and populates it. How did it know what that object ID is, or that object type is? We basically need to create an object out of the ether, and just without knowing what it is, ask it, create one of yourselves. But one of them doesn't exist. So the old interview question about a virtual constructor, of why you can't have one, I cheat and I do one, because I know what the object type is that I saved out. Pseudocode, and I'll get to the magic of how that works a little bit later, of what it does. It saved out the object ID to the stream. The object ID is basically the pointer stored in a map, and it's just an increasing number that it's stored out. So the next time, the next object I stream out, the first time will be a 1, and then a 2, and then a 3. I have some special casing for if it's actually a null pointer. You can stream out a null pointer, and you can stream back in a null pointer, and it will assign null to the pointer that you had gotten. So I have a special object ID for that. So if it's the first time this object has been saved, I add it to my ID map, and then I persist out the object ID, which is that rolling count. First time it's a type, first line is type. This one is the ID, and then I actually stream out the object. If I'm loading it, I load the object ID and say, is this the first time that I saw this object? And if no, I only need to look up the object ID in my object map and just assign the pointer back, because I know I've already loaded it. But it's assumed that I hadn't seen it before. It loads, it says first time the object loaded, then I load the object from the stream, dynamically, the object type, then I look up what that object type is and call a constructor and construct one of these objects. I add it to my object pointer, object map, and then I stream into that. So the next time coming through and it's a reused object ID, we would take the else and just pull it out of the map and ignore streaming it. So we potentially store an entire branch's complex object, which is a single value of what the object ID is. So I talked about, well, this again is what our a generic serialized function looks like. If we're saving, we stream out. If we're loading, we stream in. The base class here is a template that knows what the type is. So here's my class. It has a serialized function. It derives from a serializable template, where I'm building the chain of object inheritance. A lot of people will tell you never mix templates and inheritance and virtuals. Bunk. Once you instantiate a template, it is effectively a class. You can inherit from it. You can have it inherit from other things. It can have virtuals. It gets a little bit hairy because the object you're in, it's really hard to keep a pointer to that, since that is a mangled name that includes the types you're inheriting from. But so what we do, well, I'll actually get to that. That's buried down another step. When I create my serializable template, I take what the type name is being passed in, and I go to create a static type that has type info. The type info has a pointer to a serializable base object, which we'll hit in a second here. And it also saves a pointer to how to construct the derived object. And we store that in a type info. This stores itself into a map. This is a static function with a static map inside of it. So when this type info is saved out, I get the map, I get what my hash value is, which was the name of the object, and the class name of the object, whatever the runtime system told me that the string's name was, and it gets hashed. And I store the this for this type info, so when I have a pointer to the function to create, I can new one of these classes on the fly just by knowing the hash ID, which is what I store out in the stream for the hash, for the type ID. Contents of the serializable is a constructor function or create that knows the type that I just told it that I was passing in here. This is a my class. This serializable knows how to construct my type, and it also has the type info struct back to here. Even though this is stored in the map, this object needs to know what type it is. So as I'm serializing it out, I can say, get my type, and it will return me this information, and I can spit out the hash. When I have the hash later, I can then look it up from looking in the map and get the create function. And there's the find for when I need to create it later. Here's how the whole thing wires together. My class calls into the serializable, it gets passed in the type. The type info has each instance of the serializable has a static member of a type info that pre-main, it constructs this type info information and stores it into the map for the type info. And so all this stuff is done pre-main. It's self-registering of only the objects that you have told that you're going to need for serialization. Okay, that's where it's storing the type info, and the map has the hash, and it stores it in there. And so that's the whole thing without the arrows. So this is a slide we already saw. When we go to serialize it out, we save the type info, the hash ID. When we go to read it back in, we see it will look in each one of these data objects, and if it's a pointer, it saves out the type info. Even if it's not a pointer, it saves that out, because when it goes to read it back in, it says, am I reading in what I expected at this point to read out? Because these data have to be entirely balanced and symmetrical between data 1 and data 2. Have to write them out in the same order as you're going to read them in. It magically can't figure it out. We have to tell it what data we're storing out. In the future, when we actually have a better reflection, you can actually interrogate the class and tell it to save out all the members in there just by iterating through them. We don't have that yet, so we have to tell it what it's there. In the abstract of this talk, I alluded to some reflection, and the reflection is in the smoke and mirrors of the virtual constructor creating an object on the fly. Okay, for derived classes, the hierarchy looks very much like we did when we did just the my class, but the serializable, we have the my derived, which is this class, that goes into the serializable CRTP template, and I tell it what the base is. It then points, the base of the CRTP template would then point to my base, which also inherits from serializable, and it knows what its object type is, and the base by a default parameter here is serializable base. And it's a little noisy, but this is kind of showing what that is. A serializable base basically only has a virtual void function to serialize out or in the data. And so it's the anchor. So if anytime I want to serialize something out and I know it derives from a serializable base, I know it's going to have a virtual function for serialize. And so I can call that. And these are the derived, that it inherits from serializable, that then derives from my base, which derives from serializable again. It passes in the CRTP default constructor, or pardon me, default parameter is the serializable base. And so that's where the whole chain of inheritance anchors back at the serializable base. This has to be a concrete type. It can't be a template, because the template, the name would be mangled depending on what the parameters are. So serializable base is just a pure interface of a anchor for this hierarchy, so we know that it has a serialized function in it. And there's actually one detail on the slide that I skipped a long ways back. And I wanted to point that out because it's important here to know that if a function has this stuff at the top, this is some smoke and mirrors that you give internal to this has serialize. Basically, it says, does my class C that I'm passing in has a member function serialize? Then it basically assigns the value of yes. Yes is an array of size 1. A type of that, we don't actually have an array of that, but it says I know this is a type. A no would mean that it's a default and it doesn't have the serialized function. And so that's of size 2. So this, when I call it with has serializable of this type, it interrogates what this value is, and the value is either true or false, whether this is the same size as a yes or not. That is a magic thing that I actually only discovered 5-6 months ago. And there's lots of people who point out how to do it on the internet, and most of them are wrong about the best way to do this. And this is kind of a clever backdoor, because it's always a question of how do I know if a function or class I'm going to call has a member function that where I can decide whether I'm going to call it or not if it has a member function. And it could be for any member function. This one happens to be hard-coded for serialize. So if you wanted to do has foobar, you would actually have to make one of your own that if it has foobar. I haven't found a way to pass in a variable name for the member function. Jason can probably tell me if there's a way to do that or not. Okay, let me go back to where I was. I'm going the wrong way, sorry. Okay. So I had walked you through this data structure before. This is the arrows of all the different inheritance chain and type deduction. That it's really not ever deducting any types, but where the type chains are serializing, not stacking up to. Here, the base, there isn't a second parameter here, so it just assumes that it's the serializable base, and that's our anchor base class I was talking about. Here, we have a default, but I'm actually passing in and telling it it's my base. So when I pass it into here, it's calling my base, and then it has the serializable CRTB function. Took a little while to figure this out, and that previous set of arrows. First time I gave this talk, there was another group that was there presenting something, and we didn't discover till kind of really the night before that they were doing the same thing. And fortunately, their talk was significantly different, but we had actually internally both individually deduced the same mechanism. And actually, Daisy was in half of that talk. She's upstairs talking right now. Okay. I had talked about saving the data out to a file. I have a file source, and I can pass that into my archive. Anything you can read and write to, you can persist data to. So I have a base class that's a data source, load and save. And I can derive from that, and I make a file. It's super simplified here, but basically just write to the file and read to the file. I can do that same thing with a socket. I can create a socket that's actually as a server or a client, and the client can connect to the server, and they can live stream the data back and forth between each other, serializing in and out. You could also make your own socket source where you could write to one of the Google buffer things, and just do it in memory, or write your own memory implementation, and someone else could read it out of the shared memory. That works. Anything you can read and write from. Okay, so if it's a socket, for example, I was talking about, we create a socket source, and this is the constructor to construct a server. I pass it into the archive. Here at the same time, live somewhere, either on a different machine, different process, could even be the same process on the same machine. I construct a client. It connects to the server on a specific port. Here, when you create the server, you don't have to name it, you just tell it what port it's serving. Load those into an archive. I get the data, and I stream it out. And I wait for a response. Here, I stream it in, I calculate and make the response, and I send it back. I change the direction of the archive on the fly. At one point, it's writing out and turns around and goes to read in, and it will wait till it gets the bytes from the other side. And it streams back in. So you can calculate a response. You could do a whole series of handshaking back and forth and zigzag back and forth between these things to just handshake the data back and forth. You could do something similar in memory. Sockets will automatically wait until there's data available. And when it's assuming data is available, it's going to start climbing the hierarchy of objects that it's writing out. The other side is going to be reading in simultaneously and reconstructing that object in its memory footprint. And if the reader gets ahead of the writer, it just waits because there's no more data until there's more data in the pipeline, in the stream. This data source, since it's just a plain read and write, we can do a filter on these. And I have a very simple XOR filter that I give it a value, and I can have a file source inherit from a filter source that inherits from the data source. And so I can open a file and I can set what I want the masking code in there to be for the XOR, just to noise up the bits. So you wouldn't see whoever's going to read it has to know what that symmetrical reading XOR is, so it unmasks it when it goes. XOR is a super simple example here. You can actually use your own hashing or encryption mechanism using a full certificate and, super heavy, secure crunch up the data. Here's an example of how you would do a filter source. So I have a file source that I pass into a filter source. I give it a key. Here I just have the key that was passed in that I called a mask, which is just a byte that XORs. I stream out some stuff. A checkpoint. Internal to my stream, I keep a checksum, and you can use whatever mechanism you would want to do for it. And I write that into the stream. So when I go to read it back in, I can check the checkpoint. And it knows from streaming back in, it has a checksum of everything it read in, and then it checks what the checksum was in the stream, and those better match, or it would throw an error. And that's where the return -1. You would want to put in some nicer error handling. I cheated on that, and I didn't do a bunch of that. You can modify the mask. I increment the mask. And it does not store what the mask is in the stream. The writer and the reader have to be in sync about knowing what that would be. So when I go to read it back again, I say set mask and I increment it for what it was reading in. If you started off with the wrong key reading in, it's going to be complete garbage and you're just going to get hosed to data. And so I can check the checkpoints as many times as I wanted to. It has to match symmetrically with which objects you wrote out and which objects you're streaming back in the same order, checkpoints at the same point, because it drops a value in the stream. Another thing that I do, because I have a lot of object IDs that if I store out, chances are you're going to be reusing a lot of objects and also object IDs. And you don't want to necessarily set aside an entire 16-bit block or 32-bit block. That's going to use a lot of memory in the stream and tend to bloat your stream. As for small files, chances are that number's never going to get very, very big. Very big files, the chances are you're going to have gone all the way from 1 to, 4.2 billion, which is going to be a huge file. It's something you would have had in memory with that, 4 billion objects in it. So what I do is I actually have a dynamic int that I stream out. That I take whatever value that is and I lob it off 7 bits at a time, which is 0 to 127. And I keep lobbing those off and writing it out as long as there's a value. The top bit is a stop bit. When it hits the last value and the last block of 7 bits that has any value, I write the stop bit in there. So if I'm going to store out an object ID that is only 1 byte, or less than 127, it only takes me 1 byte. It's less than 16K minus a little bit, so I'm going to take 2 bytes. All the way up to 4 bytes, it would be 268 million. Had you actually had that many objects, you would have had a lot of wasted zeros, for the previous data. This thing will actually continue on to 5 and 6 bytes if it really needs to. If you had a real 4.2 billion uint, that would take 5 bytes to store out. I've never hit that. I've never hit anything above a 2 million. I've never bothered streaming anything out that had 2 million objects in it. Theoretically, it's entirely possible. Okay, so of all the different types we handle, we have those 4 types for the ifs, for the sniff and enable if. If it's an integral type, it's a plain type, it's serialized, has serialized, and if serializable. And then I read and write, load and save for each of those types for a reference that object, pointer to reference the array of those. But then I also have custom handler functions for if the object I've deduced is a shared pointer. If it's a unique pointer, is it a vector? Is it a list? Is it an array? And so it knows how to go through these collections and iterate through each of them. And deduce what the types are, handle them appropriately. If it's a shared pointer, It actually gets out the raw pointer of what is in there, stores that in an object ID, and it knows what the object is it's pointing to. When you go to stream it back in, you're streaming it back into a shared pointer. It reads in that object. Have I already done that? It's saved off in my shared pointer object ID map. If it's not the shared pointer, you're hosed because your symmetry's out of balance. The unique pointer kind of works the same way, but it doesn't have to worry about storing it in a shared map because you know there's only ever going to be one copy of it. A vector, just like the array, I get the count of objects and I iterate through them, saving them each out. When I go to read it back in, the vector is dynamic sized. So I pre-buffer and reserve the amount of space that I'm going to need for that and then iterate through each one of those. A list, you don't pre-buffer or pre-reserve the amount of space, but so I just end up reading them in. Array here, no one, I don't think, ever really uses a STD array just because they're not very nice and good design. In my opinion, I don't know, some people may like them, it validates the size. You have to stream out exactly the count that you're streaming back in. A map, it iterates through that and it saves out both the key and the value. So when I go to read them back in, I get what the key is, I read that in, I read in what the value was, and I store those back in the map. If those happen to have been something like a map of shared pointers, it tears that apart a layer at a time, deducing that, and potentially having the reused pointers because it was shared, so we only serialized it out the first time and not each time after that. I save strings out, both STD strings and char strings, and all else comes down to it, you have a big block of data or a blob. You can just save that out if you know it's safe to save back in. Okay, here's an example of deducing and tearing apart the types. Say you have a map of strings of vectors, of shared pointers. So the name of that would be a member shared strings to vectors of shared pointers to my base. So it's going to go through and deduce the map of a key and a value. The key is a string, the value is of a vector. The key, it saves the key out. The value, it's going to go save a vector of those types, where that type is a shared pointer, where that shared pointer is deduced to be of type my base. And then it says, is that my base serializable? And it would call the appropriately save of that type. There would also be able to, well, in this case, we knew that it was of a shared pointer. That's why it's the if serializable of type for that. If it was some other type, deduction would have automatically kicked in, and it would be, it could have been to an array of objects we were storing of whatever type. Okay, going backwards again. Okay. Operators. I had I was always showing the chevron stream in, stream out. That can get a little verbose sometimes. Sometimes you need to do it because you're going to handle your own objects, not kind of, I might explain that later. Well, actually, I better explain now. I don't think I have an example slide for it. But assuming that you have your own complex data structure that you need to reconstruct in a special way by calling some of your own application's registration functionality. You can stream back in, realize what that type is by loading that into some local variable, doing your own switch, knowing what type of data you'd had out there, and then read in the appropriate data and reconstruct that data however your hierarchy required that for what you had saved out. You'd say you had some sort of tagged data type. You were going to handle each different tagged type differently. You would have that in a switch. And you would serialize them out based on what that particular type was, and you go to serialize it back in, you serialize in the tag, you say, oh, I'm expecting this type of object, I'm gonna stream in using this branch in the switch statement for the type of objects I'm streaming in. by having all those different chevrons in and out, and 99% of the time, you're symmetric for what is being stored and what is loaded back in. So that's a little bit of excess. So that's that's a little noisy. So, but you can call a function on an object that you know is serializable. You can just directly pass that into the archive object and say, serialize this for me. And it will do what the type is and go through its deducing. You could also just use a double and operator. These are friend operators that I've defined within my archive object. And it internally says, if I'm saving, I'll serialize that out. If I'm loading, I'll serialize it in. But it takes care of the noise and the magic for you. Okay. In C++ 14 to 17, we were doing the const expert enable if, which has multiple layers. There's that has serializable. I do the const expert for setting up the detection for what each of the different types are. And then I have a using for or I bury the enable if in there. So I just say if integral type, if plain old data type, has serialization, is serializable. And then so when I set up my templates inside my archive, I template type, serializable type. If it doesn't, for sniffing a deduction, if that type is incorrect and it is not that type, that member function disappears and never existed, so it doesn't get evaluated. If it is of that type, it will be potentially evaluated for best fit. So this is how it would be set up for that. In C++ 20, we have concepts. We have to set up what the concept is. So we declare the concept of it's an integral type, a plain old data type, has serializable type, and serializable. Very much sounds the same, but we don't have to do the if on each of those. We just say load serializable type, and this is of if it were the object, a pointer to the object, or an array of the objects. We would have these same 3 different pairs of functions for load and save for each of them. For a plain data type, has serializable, yada yada. So you don't have to have all that extra noise of the if. This declares a concept, and this basically says this data type I'm expecting here would be of this type. If it's not evaluated. Okay, got a handful of examples. Do I have some questions first from anybody? Yes?
Since I thought that you've been using type ID, so is it possible that if an object is serialized with the different API that the different compiler?
Yes. The question was, if I'm serializing it out with one compiler and the type ID is of one name version, like MSVC typically always decorates classes by putting the word class in front of it. Other compilers may not do that, may have other decorations that it puts in there. That's when I get the runtime information for the type ID, it gets me the name of that and I hash that. That's where I come up with my unique name. So yes, that is true. If you're gonna serialize in and out, that has to be with the same compiler. For better safety, should be the same version. Other people's serialization mechanisms require you to use the exact same binary. I don't require that. You can compile them, if it's both MSVC on both sides, your socket server and your socket client do not have to be the same application. They only have to have the same objects that are in the serializable chain. Yeah, Doug.
I just had one quick comment and then a potentially controversial question. Your dynamic integers there with the attenuation, I believe that's the exact same format as what they call BER compressed integers in ASN1, except that it uses the 0 as a stop bit instead of 1. And also protobuf is also, they call it ARINT, and I think it's the same encoding.
Okay, so great minds think alike.
Yes.
Okay, question was, or comment, and we'll get that, and actually you should probably use the microphone so it gets recorded. But Doug was pointing out that my implementation of the dynamic uint was the same as Protobuf had used and a couple other different people. And it,
ASN1 ER compressed.
okay, yeah. So, and you had a controversial,
Potentially. Did you say you encode the integers in network order, network byte order?
a common one, and I believe I went for network byte order.
Right. Did you think about doing it instead of little endian? Just because, and this is where the controversial bit comes in, because I'm sure someone's going to tell me about their ultra spark in their basement or something. But pretty much every chip right now is little endian, right? So why not make the big endian guys do the swapping?
I can't remember actually which way I set the logic in there for that.
Okay.
And it might be, yeah, but it just needs to be common between both sides.
True.
Otherwise, if you go to the wrong architecture, wrong type of platform, you're gonna get the wrong data. However, to tie back in the point over here about the compiler, if you're on a different platform, the runtime type information may be different, may be the same. If you verified that it's the same and can trust it, you know, it works once, ship it, right? Yeah. Microphone? Well, or if it's a quick question, you just shout it out and I'll echo it back.
Well, it's actually a comment on the type ID, because it's not even guaranteed to be different for the same type on the same invocation of the compiler. So did you have anything handled for that, or did you find some
For
MSVC
the runtime
code?
type information, if you ask it for the name of,
Yeah.
Jason, is that true? That you can get the same string back for the type ID of the name of a class that's duplicate on the same compiler in the same instance of the execution?
You think get an accidental duplicate on the name?
On the name, yeah. I don't think you can.
CPP reference says there is no guarantee that,
Okay, no guarantee, but
yeah.
generally it's built off of the mangled tank name, so if, otherwise that would imply an ODR violation in my opinion, but I don't know. I've never seen it happen.
Yeah, it sounds like an ODR thing also, but I don't,
I'm not sure if namespace get mangled. If it's-
well, it actually stores it out in an unmangled name with,
The compiler.
well, internal to the compiler does, but, and actually, you don't know what the name of the type ID is that comes back. You pretty much have to depend on that it's gonna be unique. It could be a mangled, it can be decorated however it wants it. And I think you're not necessarily guaranteed between versions that are gonna be the same, but within the same version, I believe you can presume it's same.
I think the bigger problem potentially is, I can't remember the details, but a long time ago, ChaiScript actually saw the same type and two different translation units have a different type ID name. And, or, no, the same name, but they weren't comparable using type ID less than operator. They thought it was two different types. It was weird, I don't know.
Okay, so Jason Turner's comment was that he had seen classes, type IDs from different compilation units
Of the same type,
of the same type,
not comparable.
not comparable. And I could see that maybe if the type name system was based off a global table of that compilation unit, and it did, I would, however, if it was a nice human readable name, I would not think it would do that. It potentially could.
I might have been doing something really stupid like.
Well, the point
active
is,
pointers.
the point is reading.
Oh, yeah.
I've seen this, it happened to me across the DLLs.
Oh, yeah.
On Mac OS,
Yeah,
it comes up different and I had problems with that. for
the
sure.
value should be the same. The pointers could be, because it's aesthetic.
Yeah.
Okay, comment was that Dan had seen it, that it was different in different DLLs.
And I think
DLLs are a funny thing that are outside of the world of the C++ standard. And DLLs are an even funnier situation than shared libraries. However, well, I don't want to say they have seniority, but don't do that if it does that.
So, my
Yeah.
question would be, how is this working across DLL? Because
Okay, so Dan was asking if my stuff would work across DLLs.
And I have another question.
It typically should, but it may, you can't always necessarily guarantee that. Dan had a follow-up question.
Yeah, how is this different than Boost Serialized?
Boost Serialize, I don't believe can do loops, and it is not as compact of an output format. It's a perfectly valid serialize that a lot of people use. I believe it tends to more of have a back-end plug-in that most people use a JSON for the output, I believe. In my opinion, JSON is text bloat. This being in binary, it can be encrypted. Raw text out in a JSON file isn't.
Why not both is my answer. I've done serialization before where we do both. It's an option, so you can have human readable or you can have both.
You could do both. That just wasn't my target. I wanted to go for binary because because I was based on this off of what I had learned from MFC, and that's what MFC had done. So, okay, got a couple examples here. So this is just, what am I doing here? Saving it out to a file. So I generate some sort of tree. I spit out I have a little API deduction function that draws a text version of the tree of my objects. I spit it out. And because it's a shared pointer, go out of scope, my object is now gone away, out of memory. I turn around and I read it back in. So here's my little text tree. It got generated, spits it out. I go to read it back in, spits out the same thing. This node that I was saving out has the data, a left and a right pointer, which are really shared pointers. And I can just go through and say serialize out to the archive, data, and using my double AND operator, data left and right, and it persists out the entire tree and goes recursive on itself. And then I can just, serialize it out that way, serialize it back in that way. Something similar, but I have a multi-layer inheritance. I have my left and right shared pointers in the base class, and my derived type is in my data type is in the derived type. And I just do the nesting on the serialization on, but this one requires, since it's a multi-layer inheritance, you're recreating this on the fly, that it has to be using the serializable base template in both the derived and in the base. And it serializes out, climbs through the hierarchy, streams the object out, streams it back in. A network version of a similar type of thing. I create a client inside the same process, just for example. I create a server and a client, given it to the procs for the server goes out and saves out the date, actually, small print even on my monitor here for me. But what I'm doing is I actually have the server and the client in a loop where they run 5 times. One generates a node for this tree, it streams out the tree, the other one gets it, adds a node to it, and then passes it back and forth. They play ping pong, adding nodes to the tree. By the time it gets done with it and finally prints it out, I get the root that was generated on one side, and the client randomly generated a node and built it into the tree. And so client, server, client, client, server, client. And so it builds this tree that was, pseudo-sorted and passes it back and forth because when it inserted it back and forth. So it just shows that you can do a series of handshakings back and forth. Okay, more questions. Dan.
How do you address versioning?
In the stream itself, in your object, you could write out your version ID in the header of each object as you were going to stream it out. Or echo for the microphone the question, how do I handle versioning? So in the first item in a class, you could put a version number and switch on that for streaming out or streaming in. If you want to save to an old version, you would have to have a a switch that knew what the old format was and what got saved out. On the streaming back end, it would say, am I reading something that happens to be an old version? You can't stream out to a new future version because it wouldn't know that. So when you guys that was streaming back in would have to be able to read all the different versions. The other way of handling that is saying, that's an old version, I'm just going to assume that it's corrupt data and ignore it and toss it out and ignore it. So you can dynamically switch on it, and you'd have to do it manually. My archive object itself did not have that. I could foresee extending this to have a serialized where it had an array of serialized functions that would be a version 1, version 2, version 3. That would create a lot of code bloat and would start becoming very intrusive. And where it would automatically, the archive object would know how to switch between itself. So we're almost out of time. More questions?
I can follow.
Yes.
You said that when you write a variable to the archive, you prefix with the size of the variable.
Yeah.
I was just wondering if you were using the same compact integer.
Oh, when I do this, when I write out the size, that's when it's either a blob or a plain old data type of a size that has a size. Integers, the type is deduced by what it's reading and writing from, so I don't actually need to save the size out. But for a blob, it was. If you have a mismatch and I wrote out a blob that was 16 bytes and I'm expecting to read in 20, that's an error, and it's just gonna crap out.